Hello, good evening. Thank you everyone for being here. The first satellite event in the framework of Order of Operations, which is an exhibition curated and produced by Ohme, currently open at Bozar, precisely in the space of Bozar Lab, until the 11th of July. Order of Operations is an exhibition that explores the links, sometimes hidden, sometimes not so hidden, between art and mathematics. And it does so through the work of 17 Belgian and international artists that more or less consciously or more or less voluntarily use mathematics to inspire their work or deliberately explore mathematics in artistic ways. During this exhibition, we are having a series of satellite events where we gather the public to join us for a series of conversations around art and mathematics from different angles and applied in different sectors and domains of our world, our lives. As I was saying here, we are at the very first one, where we are exploring the origin of computers and the links between ancient or traditional crafts and what became digital. This we're doing it through, of course, with the angles of mathematics, and we're doing it in company of Professor Anne Dooms, which is going to be the first speaker this evening. She is Professor of Mathematics at the VUB here in Brussels. And secondly, we're going to have Amandine David, which is a designer and researcher. She's part of the exhibition, and she has quite a nice surprise for us that you can. There is a little spoiler here. Amandine works for this precise project on the relationship between weaving and coding. So I will leave the floor to Anne Dooms, our first speaker.
Good evening. Not surprisingly, my title of my talk is also the Order of Operations. And if you think of mathematics and operations, then everybody thinks of the normal operations we can do with numbers. So addition, subtraction, multiplication, and division. I will show you that there are way more mathematical operations. But these are the ones where it indeed all started with. People started counting very early. And when communities grew and people had to do or to buy stuff, we needed more and more multiplications, more difficult multiplications with large numbers. And so it was not surprising that, as people always had the tendency to make tools to help them, that it was thought about how to make tools to do these mathematical operations. And Leonardo da Vinci, the greatest inventor still of all times, was indeed the first one to think about a machine to do computations, what we call a calculator. So he made these sketches, but his machine was never built. But he thought of it to do it mechanically. So you see these rotors that actually will help you to do addition. If you think of multiplication, that's actually repeated addition. If you take 6 times something, then you can actually do that something, and you add it 6 times. So if it can do addition, you can actually already do almost everything. If we jump 100 years later, we have William Schickert. He was a German astronomer. He was the first one to build a mechanical calculator in 1620. So you can see those numbers and also these wheels. And this inspired the famous mathematician Blaise Pascal to kind of improve this machine and make the first calculator that was being sold to people. So this was the first commercial calculator. And it really worked the way that our old telephones worked. So where you have this wheel with numbers, and you put your finger in and you go to a number, and then it will rotate. So that's the way it would work. And if you added over a tenth, then it will change or it will go to the next rotor so it can change the decimal place. So this was very ingenious, but you had to be very careful in operating it. So you had to use your finger, but also the mechanics itself was a bit difficult to use. So you should not push the machine or things would go wrong. But this basically jump-started a whole new era of computations. And this was also the time where we have a lot of trips with boats, and people had to look to the stars and compute how to take the trip. And then around the same time, logarithms were invented or discovered, that's the way you want to look at it. Logarithm, actually the most important thing about logarithm is that if you take the logarithm of the multiplication of two numbers, it changes to the addition of the logarithm. So actually it can turn multiplication into addition. And multiplication is always, like I said, it's repeated addition, it's costly. So if you're working with large numbers and you have to do multiplication, that machine had to do a lot of, or you had to do a lot of operations in order to calculate. But if you take the logarithm first, then actually those multiplications are turned into additions, and then this goes a lot faster. So once these logarithms were there, people actually started to make big tables with those logarithms, and then multiplications and additions and calculations to do route planning with the stars actually went way, way better. But it was still human operation. So people, even if you had these tables to help you, in computing these tables, mistakes were made. And then if you think of, if there's one number wrong, but you take this fault into multiple operations, then this mistake can grow and can send the ship to the complete wrong side of the world. So this is where Charles Babbage comes in. So then we again jump 70 years further. He was getting annoyed by these mistakes because he, as an astronomer, was doing these calculations. And he thought, well, we have to take the human out of the loop. I want to create a machine that can do these things automatically. And in that era, we have the steam engine that was invented. So he thought to make a calculator that was steam-powered to do these calculations automatically. So you say, I want to compute this, and then the machine works. And he actually built one. You can see it in the Science Museum in London. It's called the difference engine. Why difference engine? Well, also, so it could do addition, but it could do subtraction. It takes differences, and with these differences, you can also do division. So this machine could do automatic addition, subtraction, multiplication, and division. He built several versions of it so that it could take care of larger numbers. So this is, for example, the last version that he created, the difference engine. And in order to be able to create these machines, he actually was constantly looking for money. Still, like researchers today, we're constantly looking for money in order to do our research. So he was not paid by the government, although he had a very big invention. So to look for money, he went to parties of the wealthy people. So he went to castles with lords, and he was actually putting his machine there, like we have this machine here in this nice room, give a demonstration, and then people would sponsor him and pay him to build a better machine. And so at one of these parties, he was actually talking about building a machine where, because here you could do all our mathematical operations of addition, difference, multiplication, and division. But you still had to do or give these operations to the machine, and it would do exactly what you said that it had to do. But then he thought, okay, sometimes if you do a multiplication, then depending on the outcome, you might want to do something else. If you think of programming, it's like an if. He wanted to create a machine that could deal with if. If this is the outcome, then do this. If the outcome is something else, then do this. So he wanted to create a machine that could do actually an if-then operation. And he called that the analytical engine. And so he had sketches, and he was looking for money in order to make this machine. Now, at this party, he met this lady. Somebody heard of her? I see people nodding. This is Ada Lovelace. She is the daughter of Anna Milbank, who was a lady, so she was or felt very wealthy. And she married Lord Byron, the famous poet. And so she was his daughter, but they divorced very early. She was only a baby. And they divorced because, well, he was the starter of the romantic period. He was romantic, but, well, very emotional and very, well, he could not make up his mind, so to speak. So she divorced, and her mother didn't want her to become interested in poetry or in language even. So her mother forced her to do mathematics, because she said that's the one language that is not so, or is not going to drive you emotionally. I don't think that's correct, but I can understand the reasoning. Now, at that time, girls were not allowed to study. They could not go to school, let alone go to university. But luckily, because her mother was wealthy, she could pay her education, and she hired women in order to teach her mathematics. One of these women was Mary Somerville. She was working at the university, but non-paid, because women could also not get a job at university. But she was an astronomer, and she wrote actually books about these computations like you had with the logarithm. And she made a living out of these, of selling these books. So she was her teacher. Mary Somerville knew Babbage, so they got introduced at one of these parties. Ada Lovelace saw this machine, at that time the difference engine, because the analytical engine was not built. She immediately understood the way it worked, and she immediately got from the talks that Babbage was giving how this analytical engine, this machine that could do if, how this would work. And in order to help Babbage get money, and they were thinking that he would be able to build his first prototype, like you had with the first difference engine, and she wanted to make a list of operations that she would give to this machine to showcase that it could do this if thing, and people would be very surprised that depending on the outcome it would do something else without you telling this upfront. But Babbage, he did not, so he was an astronomer, he knew a lot of mathematics, but he was not capable of teaching her the mathematics she needed for the algorithm. That's a plan of steps, of order of operations that you had to do. So she got in contact with Auguste de Morgan, a very famous mathematician in London, and they wrote these letters to each other. Because again, she could not go to university and study there. But de Morgan immediately felt that she was very smart, and so he did this teaching with her over letters. The Clay Mathematics Institute, maybe you have heard of that. They have a website where you have a list of open problems in mathematics. If you solve them, you can get $1 million. So please visit the site and get inspired. But you can also see all these letters at that website. It's very nice to see, because she is very honored to be able to have this conversation with him, but also all the mathematics that they talk about, the questions that she poses. For sure, as mathematicians, you recognize these same questions that you have during your education. Now, after all of these discussions, she came up with the first program, really a program like you would give now to a computer. A program that works with if, and that also works with recursion. Recursion is things that call themselves. So you have an operation, and it calls this same operation itself. It was a program to compute the so-called Bernoulli numbers. And if you would have or still, if you would do this by hand, you would for sure make a mistake because it's so complicated. You have to do call this, and then with this outcome, you have to do this and that. So it would, if this machine would compute these Bernoulli numbers, everybody would have been impressed. So you might think that she's world famous. Well, now we know her, but still too few people. But she was not famous at that point because even if she wrote this algorithm, she was not allowed to publish it. So as a woman, you could also not publish mathematics. So Babbage said to her, well, okay, let's do some trick. What about translating an article of my analytical engine? Because he was giving talks, but he did not take the effort to write down how it would work. And an Italian engineer had written an article in French. And Ada Lovelace translated this into English and added this program as an appendix. Yeah, that's the only way she could have it published. And actually, Babbage, sadly enough, did not find enough money to make a first prototype, so this algorithm was never run when they saw it. So we even jump now, again, big leap forward. This is a prototype that has been built, but way after, but I think more than 100 years later. And it's also in the Science Museum in London. Now you might wonder, because you have this concept of this if, but how would they do it? And this is the trick. Does anybody recognize what this is? Yeah, yeah, you can. I can. It's for a loom, exactly. It's punched cards that were used for a loom, like we have here, but this one doesn't work with punched cards because this is manually. And these punch cards were invented by Jacquard. This was 1900, he invented these punched cards because if you had to do difficult patterns by hand, again, humans might make mistakes. So this loom was also steam-powered. It's the same era. And you would give it these cards. You can, I think I have a, I know it doesn't, it works on the screen. So here, these punched cards are fed in. So it goes through, and with these cards, the machine, we will see a demonstration later, where the fabric goes through, it gets shot through, but then with the holes, it goes at different levels, and then if you shut through, you get a different pattern. But this was done automatically. And so this was actually a programmed loom, but it would still follow the punched card, so it could not do an if, right? Babbage knew that with these punch cards, he could actually turn his difference engine into this analytical engine that would be able to be programmed. Now, we already know that Amandine will connect the handcraft with the digital. We can actually turn also this loom into something digital. This is Lego Technics. Maybe you might have heard this or seen this before. Well, you can build a loom in Lego Technics, but then the punched cards are replaced by a little processor or a little computer that then actually steers all the motors, and that can actually do automatic weaving with difficult patterns that you pre-program in the memory of that processor. Now I actually want to take this loom that is pre-programmed but can do a difficult operation, and that can always do a different one if you reprogram it. I now want to show a Lego Technic machine that can do something like the analytical engine, that can do an if, that can look at a situation and not be pre-programmed to follow one path up front. It will be with a movie. So it is now inspecting a Rubik cube. You can already expect what it will do. It will solve the Rubik cube. And of course, it can be put in there in a zillion of ways. I'm not going to say the number, how many possibilities you have to scramble it. and however you put it in, it will solve it. And it will solve it because it inspects the state it is in and then knows what to do. I will let it run up to the end. So it's almost there. Voila. And actually, you can build it yourself. So we have one of these sets, and it's very addictive to let it solve your cube. Now, how does it work? Well, it's a different kind of operations than the mathematical operations that we have seen up to now. Actually, whenever you turn that cube, you can see it as an operation, and you can do it multiple times. Now, with numbers, like with 1, if you add 1, it always gets bigger. But here, if we do an operation several times, the same operation after each other, it can go back to state 1 or state 0. For example, you know, if with the cube, if one side, you turn it 1 time, turn it again, and again, and again, you'll be up and it will be in the same state. So turning your side 4 times, it will again put you in 0 state. But there are also combinations that you can do. For example, if you do this, in Rubik language, we say turn right, turn the upside, and prime means in counterclockwise, turn right, and then front. If we do this 9 times, it will look scrambled along the way, but it will turn back to the 0 state. So this is where order of operations matters, right? And what this machine does is looking at in which state he is, and then he knows, it's again with some if it's in this state, then do this and these operations until, and then it will do several things. I bring one side in order and then another side, and then that's the way it works. How you compute this, or how you make this program, is actually using group theory. Group theory is about these operations that if you do them, or well, basically that if you do them several times, that can go back to state 0. So with group theory, you can actually program a machine in an ingenious way to do this operation where you don't know upfront what will come in and it will solve it. Now, from Lego techniques to Lego blocks, this brings me to the building blocks of mathematics. And this jumps, again, 100 years forward in time. This brings us to David Hilbert. Maybe you have heard of him. It's thanks to him we have these $1 million prizes, because in 1900, at a conference, he spoke about open mathematical problems, and then people started to work on it. And one of these questions that he had was about how to build mathematics. What are the fundamentals of mathematics out of which everything can be made, out of which numbers can be made, by which you can do addition and subtraction and so on. And those building blocks are, of course, logic. And then you have logic rules, and from this, you would actually start from a number of axioms and build the whole of mathematics. If you do this, then, of course, in order to make it right, he posed some rules, some questions that sound logical again. So you don't want there to be contradictions, in the sense that you don't want something in mathematics to be true and false at the same time. It's either true or either false. And if it's true, then you want to be able to prove it with logical rules, and to show that it's true, that it follows from something else, for example. So again, sounds okay, right? And then he wanted, well, can we find out that something is true without having to construct the proof at first? But of course, mathematicians are proving things, so it would be good that if you think something is true, that you have an algorithm that can decide that it is true before you start working on it, right? So he asked, is there an algorithm that can decide in finite time, because of course you don't want to work forever, that a mathematical statement is true. And then together with the previous one, then you would know that there exists a proof. Well, you might have heard of this, but Gödel showed that those first two things, they cannot be together, so it cannot happen. And it's not about the axioms. Even if you change the axioms, there will always be things that are true, but that cannot be proven. That's strange, right? So you might think mathematicians are freaking out that there are things that are true and that you're trying to prove it, but you might never be able to find the proof. But, well, we actually don't really worry about that in practice, which is weird, but still. So it was a big statement back then. And then there was still this last thing. So, well, if you change it a little bit, then you can ask, does there exist an algorithm that can decide whether a mathematical statement can be proven? Because this would then help a bit, right? Well, Alan Turing now shows up. You all have heard of him. And actually, since, I think, yesterday, in United Kingdom, you have that the pounds have his image on. So Alan Turing is also a very famous mathematician who was not famous when he was alive, only after. And he actually worked on that last question. And he wrote his by now very famous paper in 1936 on computable numbers. What he showed is that whatever you could do with an algorithm, so whatever you would be able to compute, would be possible with a machine. A machine that he made with a long tape with zeros and ones, and this machine could do every algorithm that does something in finite time. And it can do this because it can read and write zeros and ones, and it works like this idea that Babbage had, and he actually knew the work of Babbage and Lovelace, that if it sees a certain state, then it knows what to do. So it can do this if. What makes him go further than Babbage and Lovelace is that he showed that with this concept, you can do whatever you would be able to compute. So whatever you can compute, you can do it with a machine. And by this, he came the father of the computer, because we knew that whatever we are wanting to compute, we can do it with a machine. But with this machine, he showed that there does not exist an algorithm that can decide in finite time whether something is true or can be proven. And it basically, the idea of Gödel and Turing is similar. It basically is about what we call this paradox. If you look at this sentence, this statement cannot be proven. If this is true, then this is a statement for which is true, but you cannot find the proof. So if it's true, then it cannot be proven, so it's something true that you cannot prove. But if it's false, then it says that you can prove this thing, but it says itself that it cannot be proven, so then you have a contradiction. So this idea is actually giving you this problem with the first two, and then connected with the machine of Turing, he also showed that there will be not an algorithm that can decide this. So although this was problematic for mathematics, it actually jump-started the whole era of computers. But by the time he proved that, we are almost 1940, so enters the war. So before his machine was being made, he actually went to Bletchley Park in United Kingdom and worked for the Secret Service, where they tried to break the German communication with the Enigma machine. And he built, this was the first machine he built a machine that, again, with mathematics and actually group theory, where things, order of operations matter, and where you actually look at things that after a certain time, again, become itself. And he made this machine, and they could break the German communication, and it said that it shortened the war by at least 2 years. After that, the race to make a first computer began, and he actually also was helping there at one time, but he was already one step further. Because, okay, this is now up to the engineers to build it, But he was like, also here, even if it can do, like, if I have this, then do this, if I have it, you're still, as a programmer, telling it what to do. So he was to the next step, can a machine decide itself what it has to do? So that gives his second important paper in 1950, Computing Machinery and Intelligence. You can read the first line. I propose to consider the questions, can machines think? So he was the first one to really think about, can a machine think? The title is Intelligence. So, okay, if it can think, you can say, well, if it can think, is it then intelligent thinking? But then if you read further, he also says, well, what is intelligence? What is thinking? As a mathematician, you always want definitions. These are things that you cannot define. So he says, well, instead of trying to define what I mean with intelligence, I'm going to do it with an experiment. And that's the title, The Imitation Game. And that way, I don't have to define what it is, but everybody will agree that the outcome of this experiment will say that the machine is intelligent. So you have an operator on this side, and then in two rooms, so they cannot see each other. In one room, you have another human, and in another room, you have a machine. And this operator is talking to this other human and to this machine with typed questions. And this operator has to discover whether he's talking to the human or to the machine. And of course, a machine can compute very fast. So the first thing you can think, well, I will give in 1,300,000 whatever times, and I will know whether it's a human or a machine by the time I get the answer, or if I get an answer at all. So the machine can think smartly and can say, well, I can pretend to be a human when I make a calculation mistake. That's why I cannot even multiply, or when it waits a little bit of time. So that's what he thought, okay, machines will be capable of trying to imitate human behavior. And if a computer can fool the operator in more than 50% of the time, then the machine wins what we call now the Turing test. And so he called it the imitation game. We now know it as the Turing test. So are computers capable of passing the Turing test? Can they imitate us? Because this research actually led to the field of artificial intelligence. Can they imitate us? It seems like, but you all know these things. CAPTCHAs. They were at first like these unreadable symbols, but we as humans can read it. We are very good at pattern recognition. We see what is there and we can read it. But for a computer, when there are scratches, it can actually not see it. By now they can. And why? Well, at first this was set up, this CAPTCHA stands for computer automated tests to tell computers and humans apart. So it's really this Turing test, and computers would not pass it. Why would they need it? Well, it was at the time, the 90s, beginning 2000, where everybody could freely get email. And of course, this was being exploited by crooks by let machines automatically create emails and send spam and attract people to advertisements and so on. So providers of email addresses were putting this in order a machine would not be able to solve it, and so it was being stopped to create this automatic email generation. Now, this was the first idea, but then they thought, well, we can actually use human effort in order to help machines read it. So these symbols that you saw at one point were actually scans from Google Books. You might have entered or Googled for something and you end up in Google Books. There are a lot of scanned books that you can consult on Google. And in order to make them searchable for words, it was, especially for old books, difficult to do what is called OCR, automatic or optical character recognition. And difficult things that could not be read were actually given to humans, and then humans were translating it. But then, of course, the machine gets better. right? So they needed something else, and that's what then came was these things like, I'm not a robot. You might think, okay, but then a robot might be able, or some automatic thing might be able to check that box. Well, this is actually tracking what you do with your mouse. And so mouse movements, if there's not a mouse, but it's automatically filled in, for example, then you know it's a bot. But then again, this is easily circumventable. So what we have now are these things where you have to click bridges or traffic lights or shop windows. And that's because computers can still not understand what they see on an image. So we are helping them each time when we solve what is now called reCAPTCHA, because it's a new version. So we're helping computers to see or understand what they see on an image. But now you might think, well, I've heard that AI is capable of doing image recognition. They can do face recognition much better than us. So what's going on? Well, they don't understand what is there, but they are very good in indeed recognizing patterns in images without understanding what they see. This brings me to art, right? We have this connection with art today, so I will also make this connection. Everybody, I guess, knows this painting, The Starry Night of Van Gogh. Van Gogh is a painter with a very specific pattern. You will, if you see a painting of Van Gogh which you haven't seen before, you will say, ah, yeah, it's this style, I recognize it. Well, if we feed or show a lot of Van Goghs to a computer, it will recognize this style. It will, if it sees a new one, say, well, I think it's Van Gogh. But how does it work? And how do you show an image to a computer? How does it see? Well, that's because an image is actually a large table of numbers. And those numbers are actually just reflecting the colors that the camera measured of the incoming light. So if you take a picture, you actually have your sensor, and that gets light that comes in red, green, and blue, and it gets a number, and the number is higher. It goes to up to 255. It's very light. There's a lot of light, and the lower the number, the darker, right? So this is a part of that Starry Night, and I'll show you why. I read this table of numbers into Excel, and I colored them the way that this table coloring works. And then this is what you get in Excel. So it indeed gives you this color impression. So with only these 3 colored blocks, you get the impression of blue, which was not there. So this is the way our eye actually works, and this is the way that this screen works. It actually has these pixels, which are way smaller, because if you would come closer, you would still see those cells. And that's how color works. But now you know that every digital image you're looking at is just a table of numbers. So we can again give mathematical operations, and now we can indeed think of addition, multiplication, division, but in a very smart way, in order to do computations on those images. And we can give them a lot of Van Goghs and say this is Van Gogh, and a lot of other paintings where we say this is not Van Gogh. And then this computer can find patterns, and these patterns are calculations that he makes, and that after a whole bunch of calculations, you can say, well, if I get 1, it's Van Gogh. If I get 0, it's not Van Gogh. And this is what we can do with neural networks. So this is a specific type of artificial intelligence algorithm where we can actually feed a lot of Van Goghs, and he learns the style. Then there was a next level, because now you will say, well, here, this upper thing is not a Van Gogh. No, this is a picture from over there on campus, of the VUB campus, the thinker of Rodin. The next level neural networks are actually capable of, when they get a picture, to not understand, but to detect what is shape and what is actually like color and structure. So if we give them a starry night, he will know what are the shapes that give those trees and the moon and so on, and what is the color and the strokes that it gets. And if you look at the picture above, then the leaves on the tree is again this structure, but the whole tree is the shape. So it is able to discern shape from, fill it in the color. And then you can ask him, of this neural network, to create a new image, taking the shape of one and the style of the other one. And that's what comes out here. So if I make it bigger, this is a neural network, and you can play with it online, DeepArt.io, where you can just give a painting, and you can give a picture of your own, and you can create a portrait in that style of your favorite painter. So it can recognize the style and shape and make new ones. So it can really generate new paintings. I like playing with that, and one of my favorite painters is Fadil Kandinsky. I like him because he was actually inspired by the mathematical wave that David Hilbert introduced. Because again, with Gödel and with Turing, a lot of interest in mathematics came in abstraction, and so he was an abstractionist, and he paints a lot with circles and other mathematical shapes. You might think, yeah, here we have really shapes. So what is shape? What is style? So if I give this to the neural network, and again the picture of the thinker, I get this. So again, it really captures this, it recognizes it's a style with shapes. So it really takes it. What if I take the Ghent altarpiece? What do you think? So there's a lot of detail going on. So there are a lot of shapes and a lot of structure. Well, here is where it actually goes wrong. Because here you see that the machine does not understand what is shape and what is style. So it's still a guess. And here it gets fooled by the lot of detail. So he thinks that all these faces are style, and he puts them in the tree. So again, this neural network will not pass the Turing test of can I create art? Because you can easily, again, fool him. Now, these are not only ways that you can create new content. You can actually now also speak to a machine and ask him to create new content. And one of the funny experiments that I saw lately is where you talk to a machine that actually runs GPT-3. I don't know if you heard of it. It's from OpenAI. That's the firm that Elon Musk started. So GPT-3 is sort of like a model that can work with language. So that seems to understand language. But again, it's about patterns, and it makes a lot of mistakes. But it's impressive. And it can write newspaper articles. If you give them some events, it will write a nice newspaper. It can also write poetry. And it can now, if you build such an image generating machine after it, if you talk to it, it can generate an image. So if you ask him, yeah, I didn't put this in the presentation, but you can just Google it. If you ask him, create me a chair in the style of an avocado, it will create like a nicely shaped avocado chair, so green, and you can sit it. It's very nice. But you can also ask him, give me a picture of the Leaning Tower of Pisa. And then you get this. So, still much work to do. And that's exactly what we do in our research group, Digital Mathematics, and at our Department of Mathematics and Data Science. We are creating new mathematics to help machines understand better what is going on. Not to be better at us, but in order to help us. Again, machine is always a tool to make our life better. And we are working on how to teach computers the order of the operations it should do. Voilà. So.
Have you ever tried the Deep Dream, Deep Intel, deep making art online thing, it originally developed by Google? Yes.
My question is, in your life, do you have artistic practice yourself? Or are you doing art, like music or painting? Or
No. I need to repeat the question because of the recording. So the question was if Professor Andums is actually somehow having any artistic practice in her life.
Yeah. Well, thank you for that question. But although I really like art and I'm in awe for craftsmanship, I cannot do it. And that's probably why I like it so much, and that's probably why I like to do it with a computer, because then I don't have to do it myself. My hands are never doing what I want them to do, but my machine I can do.
So you have been collaborating with the Musée des Beaux-Arts?
Yes, yes. So we have been using mathematics on a painting of Kokoschka, which is actually was in need of restoration. So with mathematics, we actually looked at what restorations have occurred, and then we applied this also to Madame Babbage of Gauguin. And this really helped the art historian to look at which zones were most likely overpainted, which was original, also looking at the style and helping the restorers. So it was very nice. I would never be able to touch the painting, but digitally again, yes.
Well, that is extremely fascinating. Any other question? Yes.
Thank you, Professor. I have a question. Why do you think there is so many people that put a lot of hope in artificial intelligence, that believe that it's super creative, intelligent, whereas we understand from your presentation that it still does reasonably what we tell it to do?
Okay. So the question is why, in your opinion, there are so many people getting so enthusiastic about artificial intelligence, while we see that we're still very early stages. And I would allow myself to add actually a quote by Kate Crawford that you surely know, who stated very clearly artificial intelligence is neither artificial nor intelligent, which I think says a lot.
Yes.
Please.
Well, I think we can actually look at the way Babbage worked, because in order to improve it, you would need more money to do research. So that's one side. People will hype it in order to get more money in order to improve it. But on the other hand, you also have people that see opportunities in making people scared about it, and that it will take away jobs, because it will give you a disruption and a change in the way the economics work. So there are two sides to this hype. It's somehow a hype, but I still believe that there is so much room for improvement, and that we can indeed make it better. But, and that's some discussion that Alan Turing took up, Ada Lovelace also in one of her appendices, she wrote that she thinks machines can do things on themselves, are able to learn, but that they will never be creative. And Turing refutes that, and he says, well, no, she's wrong, they can be creative. But at the moment, and I still believe it will be like that, we are still the ones running it. So even though we let it seek for patterns itself, it's still following an algorithm and an order of operations that we give it. And I don't see it like changing that. And if it changes what order of operations it's doing now, it will still be us still telling it how to do that change itself. So I don't think it will be creative, but it's the one that steers the machine. Voilà.
Okay, well, thank you very much. One last chance for asking your question. Okay, we're going for a break. We have about a 20 minutes break before welcoming Amandine David on the stage. You can have a drink. You can order it at the bar, but you're gonna have to drink it downstairs, unfortunately, because of COVID. So we eat 6+7, so we're gonna start again at 30. Okay, 7:30 here for the second part of the event. Thank you very much, and thank you, Professor.